In the 12th lecture, we will cover the linear regression and the ordinary least squares method. In statistics, linear regression models the linear relationship between a dependent variable and one or more independent variables. The case of one independent variable is called simple linear regression. The simple linear model is EY equals to beta 0 plus beta 1 multiply x. Here, the y is the dependent variable, x is the independent variable, and the epsilon is the error. For more than one independent variable, it is called multiple linear regression. The multiple linear model is this. Here, P is the number of independent variables as predictors. The linear regression is linear in parameters. For example, EY equals to beta 0 plus beta 1x squared is a linear regression model since the parameters beta 0 and beta 1 are linear with the expectation of y. And EY equals to beta 0x to the power of beta 1 is not a linear regression model because beta 1 is not linear with EY. Correspondingly, nonlinear regression uses a nonlinear function between the dependent variable and the independent variables. Some nonlinear functions used in the nonlinear regression model include exponential functions, logarithmic functions, power functions, Gaussian functions, and etc. In general, there may be no closed-form estimations in nonlinear regression, but some nonlinear models can be transformed to be linear. Regression analysis is widely used in prediction and also can be used to infer the relationships between the independent variables and the dependent variable. Linear regression has several important assumptions. First, linearity. The regression model is linear in parameters. If the relationship between any independent variable and the expectation of y is nonlinear in parameters, then the linear model may not be valid. Second, independence. A random sample is required, and the observations are independent of each other. Third, homoscedasticity. This assumption is also from random sample requirement, and the errors have constant variance. Specifically, the variance of the error is the same for any value of x. Fourth, normality. The errors follow a standard normal distribution. Fifth, no high multicollinearity. The independent variables are not highly correlated with each other. These are the basic assumptions, and we may have some other assumptions related to these assumptions. For a simple linear regression, the population regression function is this. Here, capital N is the population size. Beta 0 and beta 1 are parameters, and epsilon I is the error. We may estimate the parameters from the sample, where we have n pairs of xi and yi values. Then we have the sample regression function as this, with B0 and B1 are the estimators for beta 0 and beta 1, corresponding to the intercept and the slope of the estimated regression line. EI is the residual, which is the difference between yi and yi hat, where yi hat is the estimated or predicted value of yi. Now, how do we find the best fit line and determine B0 and B1? The right graph shows 6 pairs of x and y values as an example. It is hard for us to decide from graph whether the best fit line is a red, black, or blue line. The least squares method suggests that the best fit line minimizes the residual sum of squares RSS. In ANOVA, the residual sum of squares is related to the difference between the observed values and the group means, and represents the within-group variation that may not be explained by the model. In linear regression, RSS is related to the difference between the observed values and the estimated values, representing the variation that may not be explained by the model as well. It turns out the black line is the best fit line since the sum of squared residuals is at the minimum. At the minimum, the derivatives of RSS to B0 and B1 are equal to 0. Thus, we may analytically derive B0 and B1 from these two equations. The first equation gives B0 equals to y bar minus B1 x bar, and substitute it in the second equation. Then we have the estimated slope B1 is this. Since the numerator is related to the sample covariance between x and y, we may further simplify B1 to the sample correlation coefficient Rxy, multiply the sample standard deviation Sy, and divided by Sx. After we get B1, then we may substitute it back into the first equation, and we have the estimated the intercept B0. After we have estimated the regression line using the least squares method, we may get the residual sum of squares. As discussed in Lecture 4, if the population variance sigma square is unknown, then we may estimate it with the unbiased estimator S square. For linear regression, we may do it similarly with S square, defined as mean squared error. In simple linear regression, S square is RSS over n minus 2. Here we have n minus degrees of freedom since we lost 2 degrees of freedom from the 2 parameters in y hat. In multiple linear regression, S square is RSS over n minus p minus 1, and the p is the number of independent variables. The following table connects the sum of squares from a random sample to ANOVA and regression. Here, the total sum of squares is the sum of explained sum of squares and residual sum of squares. If we have a sample without any model, then we have the total sum of squares only. As we learned from the sample variance in Lecture 7, total sum of squares has n-1 degrees of freedom due to the sample mean. In ANOVA, K is the number of groups and Ni is the size of group I. Similarly, the explained sum of squares has k-1 degrees of freedom for k groups. Thus, the residual sum of squares representing the variation cannot be explained by the model has n-1 minus k-1, which is n minus k degrees of freedom. In linear regression, P is the number of independent variables, and yi hat is the estimated outcome I. The explained sum of squares has p degrees of freedom, since yi hat has p plus 1 degrees of freedom due to the intercept, and the sample mean has 1 degrees of freedom. Thus, for simple linear regression, the model has 1 degree of freedom. Since the total sum of squares has n-1 degrees of freedom, the residual sum of squares has n-p minus 1 degrees of freedom. If we define k as the number of parameters in regression, then k is p plus 1 including the intercept. Thus, we may align ANOVA and the regression models. The table connects the ANOVA tests and the regression and gives an intuitive explanation about the definition of mean squared error. In machine learning, sometimes we may use RSS divided by n as the mean squared error, which is a biased estimator in statistics. This slide is an example of the simple linear regression. We try to find out if there is a significant association between the household income and the household expenditure in 2018 in a small community with 30 families. The unit is $1,000. The SAS data set is on the left. The average expenditure is $60,733, and the average income is $87,800. The regression results by SAS are shown in several tables. The first table is the analysis of variance. We may remember in the ANOVA test that independent variables should be categorical. Although the ANOVA procedure in SAS does not allow the continuous independent variables, the REG procedure gives the ANOVA test results, and we may also do the ANOVA test in a more powerful procedures such as PROC-GLM. Even the independent variables are continuous. Here, we find the degrees of freedom for the sum of squares. As learned from the last slide, the number of total degrees of freedom is n-1, which is 29. The number of model degree of freedom is 1, since there is only one predictor. So, the number of error degrees of freedom is 29 minus 1, which is 28. The mean squared error, MSE, is RSS divided by the error degrees of freedom, which is 642.77. We divide the mean squared model by the mean squared error and get the F value of 113.45. Since the p-value is less than 0.0001, the model is highly significant. There are several important model measures in the second table. The first one is root MSE. Root MSE is the square root of the mean squared error. The second one is coefficient of variation, which is the root MSE divided by y bar. It is unitless and measures unexplained variation in the outcome. The coefficient of determination R squared is the most commonly used measure of the goodness of fit of a linear regression model. It is the ratio of the explained sum of squares to the total sum of squares, known as the proportion of variance explained. The coefficient of determination equals the square of the sample correlation coefficient between x and y in simple linear regression. In multiple linear regression, it equals the square of the sample correlation coefficient between y and y hat. The adjusted R squared accounts for the R squared inflation when more independent variables are added in the model. It is defined as this, where DOFE is the error degrees of freedom and DOFT is the total degrees of freedom. Adjusted R squared is more appropriate in multiple linear regressions. The third table is the parameter estimation. In this example, the estimated intercept B0 is 14.9, and the standard error for B0 is 8.26. The standard error may be calculated from the formula here. The ratio of these two is the t-value, which is 1.8. And the p-value is 0.08 for the two-tailed test. Thus, the intercept is not significantly different from 0. If we are interested in a one-tailed test, then we may simply divide the p-value by 2. Similarly, B1 is 1.2, and the standard error for B1 is 0.11. The standard error for the slope may be calculated from this. The t-value is 10.65 and the p-value is less than 0.0001, which is highly significant. At the 5% significance level, there is enough evidence to conclude that there is strong positive association between the household income and the household expenditure. In summary, we learned the linear regression model and the least squares method. Linear regression models the linear relationship between a dependent variable and one or more independent variables. We have simple linear regression if we have only one independent variable, and multiple linear regression if we have more than one independent variable. Nonlinear regression models the nonlinear relationship using a nonlinear function, and the sum can be transformed to be linear. The linear regression model has several important assumptions. The model is linear in parameters. The errors are independent, have a constant variance, and follow a normal distribution with a mean of 0. The independent variables are not highly correlated. We may estimate the parameters in a linear regression model using the ordinary least squares method. The error variance in the model may be estimated by the mean squared error, and the goodness of fit of a linear regression model is commonly measured by the coefficient of determination R squared.